In this video, I'm going to talk about some of the more common reactions of the halogens. And of course, we've already discussed several reactions involving halogens because in the metals sections of the course, we saw that all of the different metals we looked at reacted with halogens. We saw that, for example, if we had sodium metal and it was exposed to chlorine gas, that we would get sodium chloride, which is a solid. There's no water here, so nothing is aqueous. And in order to balance that, because we have two chlorines in our diatomic chlorine molecule, we need two sodium chlorides and therefore two sodium metals. And on the slide in front of you, you can see some other beautiful examples with nice pictures showing the reactions going on. And in each of these pictures, you can see a fairly vigorous reaction. In the top one, we can see that we add our chunks of metal into our flask, and now there's all sorts of fuming going on before we eventually settle out to our product with the white smoke just from the formation of that aluminum bromide solid. And in our bottom reaction here, we can see that we take our chunk of metal, and when it goes into the flask of chlorine gas, it starts to glow red because of the vigorous reaction between the iron metal and the chlorine gas. So reactions between metals and halogens tend to be extremely favorable. The halogens do react with several nonmetals as well, though. If we were to take elemental phosphorus, for example, in this case you're seeing P4, which is white phosphorus, and if that were to be exposed to chlorine gas, which is what this experimental setup is showing, there is chlorine gas coming in through that tube, we get rather a violent reaction over here as phosphorus trichloride is produced. And if we wanted to write out a balanced reaction equation for that, we could do so. We would have our P4 and our Cl2 to give PCl3, and then we need to have 4 phosphorus trichlorides to match the 4 phosphorus atoms in the P4, and that means we need 6 molecules of chlorine gas to match the 12 chlorine atoms on the product side. If we were to add even more chlorine gas, we would then get PCl5 from our PCl3. But we never ever get PCl4. And one way that we can predict products of reactions between nonmetals, if we don't have experimental data allowing us to figure it out through stoichiometry, is by attempting to draw the Lewis diagrams for each of the potential products. So if we wanted to predict what we might get from the reaction of phosphorus with chlorine, and we wanted to consider PCl3 as an option, and we wanted to consider PCl4 as an option, and we wanted to consider PCl5 as an option, we could attempt to draw the best Lewis diagram that we could for each of those species. So recall that a phosphorus atom has 5 valence electrons, and each chlorine is going to have 7 valence electrons. So if we have 3 of them, then that's going to give us 21. And when we add that to the 5, that's going to give us 26 electrons to play with. And so if we want to draw a Lewis diagram for PCl3, we can do that. We start off by connecting our 4 atoms together. That has used up 6 of those 26 electrons. Then we fill in lone pairs around the chlorines, like so. That uses up another 18 electrons. We've got 2 left. They go on the phosphorus. And we get a really nice Lewis diagram in which all 4 atoms obey the octet rule. If instead we wanted to draw PCl5, we could do that. So we would have 5 chlorine atoms, which is going to give us 35 electrons, which we add to the 5 from the phosphorus, giving us a total of 40. We put our phosphorus in the middle. We draw some chlorine atoms around it. That uses up 10 of our 40 electrons. We've got 30 left. And if we start filling in lone pairs on each of our chlorine atoms, drew those two a little bit too close together. You can see that with our 40 electrons, we have generated a Lewis diagram where everything has a neutral formal charge. The phosphorus atom in the middle does violate the octet rule, but phosphorus is large enough that we're comfortable doing that as long as it has a neutral formal charge. And PCl5 is absolutely something reasonable to draw. If, on the other hand, we want to draw PCl4, then we're going to have 4 chlorine atoms, which is going to give us 28 electrons for the chlorines. Add the 5 from the phosphorus, and we get 33 electrons with which to draw our Lewis diagram, which should probably be our first sign that this Lewis diagram isn't going to go very well, because we have an odd number of valence electrons to work with. And that means something is going to have an unpaired electron, and something isn't going to obey the octet rule. And so my best shot at doing that, I would again put my phosphorus in the middle, attach my chlorine atoms around, like so. That uses up 8 of my 33 electrons, so I got 25 to go. So I will start filling in lone pairs around the chlorines, and that uses up another 24. So now I have 1 electron left, and the least bad place I can put it is on the phosphorus, which at least gives the phosphorus a neutral formal charge, but it's got an unpaired electron. I don't like this Lewis structure so much. And as it turns out, phosphorus tetrachloride, not a thing that really exists on a regular basis. Phosphorus trichloride, on the other hand, and phosphorus pentachloride, both species that are relatively straightforward to make. Whereas phosphorus reacts with halogens to give 2 products, sulfur reacts with halogens to give an awful lot of different kinds of products. And if we were to try a similar analysis attempting to draw all sorts of potential Lewis diagrams, we can very quickly see why this is. Sulfur exists in many different allotropes, but one of the most common is S8, which essentially is a crown, so a ring of 8 sulfur atoms, kind of like so, each of which has 2 lone pairs on it. You can fairly easily imagine starting to do things like break open spots in that chain to insert chlorine atoms, and everything will work just fine and still obey the octet rule, even though these are some really ugly Lewis diagrams. And so you can draw Lewis diagrams that work for a myriad of different compounds containing sulfur and 1 or more halogens. And so if you take a pure halogen and you react it with sulfur, you're just going to have to control exactly how much halogen you use in order to control what your product's going to be. And so you can do anything from taking your sulfur and reacting it with a very small amount of chlorine gas to get a product like disulfur dichloride. And if I wanted to write a balanced reaction equation for this, to make my sulfurs balance, I need a 4 here, and then to make my chlorines balance, I need a 4 here. So 4 molecules of chlorine gas for every molecule of the sulfur. On the other hand, if I wanted to use a lot of chlorine gas, I could make something like, say, sulfur hexachloride. And in order to balance this, again, I need 8 of my product to deal with the 8 sulfurs from the allotrope of sulfur that I chose to use. And that means I'm going to need 24 molecules of chlorine gas for every sulfur. And there's a whole lot of other options in the middle there. Finally, I'll take the opportunity to remind you that we've already seen another reaction of chlorine gas in the alkali metals section. We saw that when we use the chloralkali process to produce chlorine gas and sodium hydroxide, that if we don't keep our products separate, that what we wind up making is bleach. along with some chloride ions and water. And to balance this, I need 2 hydroxides. So here I'm just reminding you of a reaction that we've already seen. And in terms of the industrial production of chlorine gas, well, you've seen that too. That's the reaction that you already saw for the chlor-alkali process, which produced sodium hydroxide. So it was the electrolysis of aqueous sodium chloride, meaning we had water around, to give aqueous sodium hydroxide and chlorine gas and hydrogen gas. And in order to make this balance, we needed 2 sodium chloride and therefore 2 sodium hydroxide and therefore 2 water.